Is my hello? Welcome to Matsuyama. Thank you. Yeah, I'm going to present my slides. Hello from Matsuyama. This is the first time for me to visit Matsuyama. I'm really excited to be here. I am Uchio. I'm from Fukuoka, and I'm a product engineer at Smart HR, which is a RubyKaigi Platinum sponsor. I have two things to advertise. One is about Satoru and my book. If you are interested in Evo and why fractals talk, I believe BPF is also helpful. Give a shot at the lunchtime. And our company, Smart HR, is hiring product engineers who love Ruby around Japan. Okay, today's topic is Rodite. What is Rodite? It is a WebAssembly or WASM runtime written entirely in pure Ruby. Rodite is named after the rare mineral rhodite, which starts with letters W and A. It's a standard Ruby gem, so you can simply run gem, install Rodite, and start using it. You can also use Rodite as a library to load and interact with existing WASM modules directly from your Ruby code. So let's have a look at WebAssembly. WASM is a binary instruction format. It is originally for browsers, but WASM is now designed to run anywhere: servers, edge devices, embedded systems, and yes, inside other applications. Here's a simple WebAssembly example. This C code, as you can see, just performs addition. If you compile this code into WASM binary and then write this JavaScript in the browser, we can verify that the addition function originating in C is now running successfully within a browser. Okay, here's the flow of how a WASM program works. First, prepare source code such as C, Rust, then compile it into a WASM binary. Finally, execute the WASM binary via a WebAssembly runtime. Browsers have built-in runtimes, and there are standalone ones for terminal, like WASM Time or WASM Edge. Now let's return to the topic of Rodite. It's a WASM runtime for the Ruby ecosystem within Ruby. Since it's written in Ruby, you can run WebAssembly within Ruby. A key design principle is its purity and portability. Rodite depends only on Ruby's standard libraries. No external C dependencies or gems. This means if you have Ruby, you can run Rodite, maybe even on mRuby, JRuby, or other Rubies in the future. Currently, Rodite has a near complete implementation of the WASM core specification, very basic WASM support. WASM core spec covers the fundamental instruction set, types, and memory model need to execute compliant WASM files. Crucially, Rodite also implements WASI, the WebAssembly system interface, especially the common preview 1 version, supports common preview 1 version. The core WASM spec doesn't define how to interact with the outside world, such as file systems or clocks. WASI provides that standard interface. It allows to run more complex applications compared to WASM, including Ruby itself compared to WASM. So why do I build this? There are several reasons. First is to expand integration between Ruby and WASM. The primary goal is to unlock the potential of WASM's power within Ruby applications. Then I required high portability. I wanted runtime that works whenever standard Ruby works. For comparison, consider other solutions such as WASM times RB. During installation, these gems require either building native libraries or using pre-compiled artifacts called file gems. These requirements can potentially increase operational overhead depending on the environment. So furthermore, separate processes are needed for different Ruby implementations, like CRuby, MRuby, or JRuby. Writing WASM engine in pure Ruby provides greater mutability and compatibility. And third one is leverage WASM's strengths into Ruby ecosystem. Fundamentally, WebAssembly offers compelling advantages. But honestly, the main reason was that I wanted to play with a complicated problem with Ruby just for fun. So, in my opinion, WebAssembly holds significant potential due to several key strengths, such as language agnostic nature. It serves as a compilation target of many languages like Rust, Go, C, Prefix, and C-based languages. Also, it's embeddable and portable. Since WASM is relatively small, it's embeddable anywhere. I think it's helpful to view the browser itself as just one prominent example of an environment embedding a WASM runtime. And finally, it enables polyglot systems in the future. Combining languages with embeddability allows developers to build applications by combining components written in different languages. The diagram on the website of WASM Cloud, which is an open source WASM apps orchestration, gives a good sample. In essential, WASM's value extends well beyond just the browser. Okay, now that you understand WASM's background, let's dive deeper. Okay, sorry. Let's look back at the development process of WASM. There are several milestones during WASM's development. I'm going to describe them in order. The first milestone was porting concepts from a resource called Gorilla Book and getting hardware to run WASM. Gorilla Book is so named after the author's pen name. It is a webbook originally written for learning the basic implementation of WASM using Rust. But I decided to implement a Ruby version for study, and that's how it started. It's an excellent book, but understanding the overview design of the VM was quite challenging. However, the book itself includes Rust reference implementations, which was extremely helpful. Let me briefly explain the internals. First, you must parse the wasm binary. However, the binary format is quite simple. Here's a diagram. It starts with some preamble, then hits a header, which contains the type and size, followed by the content of various sections. Once the binary is parsed, the next step is just running a VM. The VM implementation is also fundamentally a loop. Fetch the current frame and instructions, execute it, then fetch the next one. This snippet is almost a real ordered code. Conversely, while the VM is simple, interacting with the outside world, like handling output, is a bit more difficult. To produce output, you must implement at least the body function, fd, right? After that coding, hello world worked. Okay, next, I decided to cover the basic instructions of the wasm core spec. At this point, I have a slight desire to run ruby.wasm. The wasm instruction set has a basic range and extension sets. The core spec defines which instructions belongs to which range. There are special extension sets for things like this is simid and others. This time, I focused only on the basic parts. You can refer to the opcode table website to see which instructions are included in the basic set. Even focusing on the basic part, I had to implement 192 instructions. However, each VM instruction is relatively small. By the way, wasm has 4 numeric types: I32, I64, float 32, F64. Often similar instructions exist for each of these types, like addition or subtraction. For these common instructions, I created a generator to produce them collectively. I created a very simple template like this. Here's the generated code. Okay, with the basic instructions covered, I thought about running a more practical program. This led to the grayscale journey. I tried running a Rust program for grayscale conversion that I had created for another project. But it didn't work. Thus began the days of debugging. Briefly, the grayscale program takes base64 encoded data, like data URL, decode it to the result as a PNG, and converts it, re-encode it, and finally encode it back to base64 text. The first issue I encountered was that the memory allocation process. The fix was just one line, but it took some hard effort. Memory issues were fixed, but it still didn't work. The problem was that Rust panics are translated into a wasm unreachable. Unreachable simply means make error if reached, which was very helpful for debugging. So instead of letting panic, I modified it to return the error string directly from the function. Okay, now I had an error ID and message. So I looked at the Rust PNG library code. I'll say I'm not sure. This part was clearly decompressing or deflecting based on the function names. But I wondered if I had to study the deflect algorithm from scratch, which felt a bit daunting. But looking at the code, I could see that bit shift operations were heavily used. So I decided to first verify if the bit shift and other numeric instructions were correct. The correctness of numeric instructions like I32 can be verified using the official WASM test sheet. Here are testing process. The official WebAssembly test sheet is provided in a format called WASD. Using a command called WASD2JSON, you can generate JSON files describing the test case along with the corresponding WASM binaries needed for testing from WASD files. Each test case specification in the JSON includes input values or expected output. Testing then simply involves executing the WASM binaries according to these JSON specifications. Doing this with Ruby is straightforward. So when I first ran the test cases related to I32, several tests failed, including bit shifts, as I somewhat expected. After fixing all of these failures, I was able to get the grayscale to run successfully. It's working correctly, right? Looks like the expected examples. This gave me the momentum to run something even more practical. Yes, ruby.wasm. Running ruby.wasm requires proper WASI support in addition to the instructions. Building ruby.wasm with default options requires 37 WASI functions. I started to implement these 37 functions, grouping them into a single class. As an example, implementing clock time get essentially just wraps Ruby's time.now. It might look a bit odd, since it's just bridging the WASM world and the OS world using Ruby, but it's an essential process for runtime. Thus, the tasks became diligently implementing these WASI functions one by one. My strategy was simple. Repeatedly try to launch ruby.wasm. When it failed saying function foobar is missing, I implemented that function again, start a loop. So the functions implemented were truly basic system instructions, getting arguments, count time, random numbers, environment variables, or file descriptors operations. After some of these functionalities were implemented, the ruby.wasm version option started working. At this stage, Ruby's embedded core library worked, so things like integer times can run correctly. So nice. However, even though it could handle basic standard I/O, the file system wasn't recognized yet. This meant required didn't work correctly at this time. Loading warnings appeared. So the next step was to make require work correctly. To do this, we would need to recognize the file system collectively. So I tried implementing the file system handling functions. Initially, I crudely tried to make path open function work, assuming it be called, but that function wasn't even being called. Why? Because I need to correctly implement the pre-opened mechanism first. Now I'll try to describe overview of pre-opens. By default, a WASM runtime, even with WASM enabled, can't access the host environment file system at all for security reasons. When launching the WASM runtime, information about the host file system to be shared must be passed via pre-registered file descriptors 3, 4, 5. After initialization, when runtime is going to access the file system, it must check these pre-registered file descriptors first. This mechanism is often referred to as pre-opens or pre-start. Looking at the WASM SDK's libc implementation, you can see specific processes. Inside the WASM SDK, before a program attempts to open a file, a function named WASM libc populate pre-opens is called. Within that function, it iterates through file descriptors, attempting to retrieve information about pre-registered host file system entries. If it successfully retrieves information, it registers the mapping between the guest path and the corresponding host path. It continues until it encounters an error. Actually, functions like path open are implemented such that if no relevant pre-open information has been registered, they won't even attempt to call the underlying internal WASM function. So I implemented the necessary functions related to pre-opens. After all that, standard Ruby command started without any loading warnings, right? So all's well that ends well. However, in my environment, initializing all of Ruby gems takes about 70 seconds. This leads into the final topic, performance. Now that we saw ruby.wasm working, let's talk about performance measurements. This is still ongoing work, but I hope it's informative. Here are benchmark topics. Unless otherwise noted, I'm using grayscale benchmark. The software versions are as listed. Let's start with improvements to block jumps. WebAssembly's jump instructions are a bit unusual. Instead of instructions holding fixed offsets, the target end position is calculated dynamically. This was done in a method called fetch offset by end. This method was dynamically calculating the corresponding end position every time if block or loop instruction was encountered by peeking ahead at subsequent instructions. When I provide the very first implementation of Ruby with RubyProf, this method was consuming a lot of time. Since the calculation happened inside functions called repeatedly, it would naturally be slow. So assuming that instructions aren't dynamically written, I pre-calculated the end positions and cache it. After passing the instruction once, I iterate through them again, calculate the end positions, and catch them. This change reduced execution time by 43% for the grayscale benchmark. Next is instance creation, profiling raw data using a perf. Identified bottlenecks like RBVM set ID or RB class new instance path keyword. Here's an excerpt from the perf results. The problem is that it's creating a way too many object instances without internal representation for types like I32 uses a simple class, but creating these repeatedly is slow. How many? Using trace points on the grayscale benchmark, I found it creates about 18.8 million integer objects in grayscale. I tried a simple experiment memoizing frequently used integer instances. I memoized values from 0 to 64 and -1. This did result in a speed up about 1 second in a measurement. Note that the result includes a commit that eliminates some object type calls. However, ideally, immediate values should be used for integers and floats, but this requires significant design changes, so it's marked as a to-do. Actually, I heard object new is going to be faster just yesterday. There are some more to-dos. For example, addressing ruby.wasm starting time. Purging the binary file itself accounts for over half of the startup time. So there might be room for optimization. On the other hand, the impact of interactions with WASI function appears to be relatively minimal. Last pick is, does WASI help? Yes, it's extremely effective. And how effective? On my ARM environment, compared to running without WASI, Ruby 3.1 showed about 52% improvement, and 3.4 shows 57% reduction in execution time. Thank you always to the budget team. Before I conclude, I'd like to present a demonstration. Whoa. Right. でな。これでいいかな。はい。This took about maybe 20 seconds. And I used disable gems for speed. Yeah. Okay. So the conclusion, to conclude, while summarizing, let me mention one more thing. There's a next edition wasm format called the component model. I'd like to support it eventually because I believe the component model will further enhance wasm language agnostic nature, which I discussed earlier in today's talk. And I'd like accept contribution if pull requests come in. Running was runtime. Purely in Ruby still feels quite like board adventure in some ways. But I'm going to challenge. Thank you very much for listening. Acknowledgements. And this I want to I want to introduce the haiku from Shiki Masaoka, who is the founder of modern haiku, and from Matsuyama. And this haiku is about sakura and hangover. I have a little hangover. So let's enjoy the final day drink up with respect to Shiki. Thank you.